Standardized tests must be both reliable and valid. Reliability refers to the consistency of repeatedly. Standardized tests must be both reliable and valid. Reliability refers to the consistency or repeatability of the measuring instrument. In other words, does the test consistently show what the child can do, or do the scores fluctuate wildly from one occasion to next? It's important to note that reliability doesn't mean a child IQ scores will never change. Scores often go up or down as children develop and can be influenced by factors like fatigue or developmental sprouts. Reliability refers to the short-term consistency of the measuring instrument itself, not the child. Major childhood IQ tests, such as the Stanford Binet and Wechsler tests, are known for their good reliability. Validity, on the other hand, refers to how accurately a test measures what it is intended to measure. Criterion validity looks at whether scores on a test relate to performance on some external criterion. For example, the Stanford Binet test correlates at about 0.5 with academic performance and other standard measures of cognition. It also correlates with indicators of job status and performance in adults. Let's dive into two different ways of thinking about intelligence. First up, imagine intelligence as a single, all-encompassing trait that we all call general intelligence. If this is the case, it doesn't matter what specific task we use to measure it. People with high general intelligence will excel at any task, while those with lower general intelligence will find all tasks challenging. This would mean that different measures of intelligence will show consistently high correlations. Now, let's consider a different idea. What if there is no such thing as general intelligence? Instead, there could be various specific intelligences, like verbal, mathematical, and spatial intelligence. In this scenario, people might be great at one type of intelligence, but not so good at others. If we test for these different forms of intelligence, we will not see uniformly high correlations. Instead, tasks measuring the same type of intelligence would correlate strongly with each other. For example, verbal tasks would correlate well with other verbal tasks, but not so much with spatial tasks. Charles Spearman, the inventor of factor analysis, introduced what we now call the two-factor theory of intelligence. According to him, one factor is general intelligence, or G. In Spearman's view, G intelligence, every type of intellectual ability, and its K determinant of individual differences on any intelligence test. The second factor is C, which stands for specific abilities that contribute to performance on particular tasks. However, not everyone agreed with Spearman. For instance, Louis Thurston developed an intelligence test to assess 7 primary mental abilities: verbal comprehension, verbal fluency, number, spatial visualization, memory, reasoning, and perceptual speed. Thurston believed these 7 abilities were largely independent and equally important. And 7 is just the beginning. Google Force structure of the intelligence model proposed at least 180 distinct mental abilities. Talk about a complex view of intelligence. So, how do we resolve the debate between general and specific views of intelligence? Often, the truth lies somewhere in between the extremes. The consistent finding of positive correlation among different measures of intelligence suggests that something like general intelligence does exist. However, the fact that these correlations aren't perfect indicates that more specific subskills also play a role. This brings us to the hierarchical model of intelligence. Imagine intelligence as a pyramid. At the top, we have broad general abilities. Below that, we find more limited specific skills. This model aligns with both the theories proposed by researchers like Spearman and our everyday intuitions about intelligence. Most of us can rank people, including ourselves, along some general dimensions of intelligence. But we also recognize that everyone has different strengths and weaknesses. You might excel in one area while a friend shines in another. This hierarchical model captures that complexity, showing how broad abilities and specific skills coexist and interact. Do children's IQ stay the same as they grow, or can they change? For instance, if a child scores 100 at age 4, will they score the same at ages 8, 12, or even 20? First, traditional tests of infant intelligence don't predict later intelligence very well. For example, the correlation between performance on the Bailey scales and later tests is typically close to zero. There are exceptions. Very low scores on infant tests can sometimes indicate developmental problems, and scores on specific subparts of an infant test, like fine motor skills, may relate to similar skills in childhood tests. But overall, individual differences in infant scores don't tell us much about how children will differ later in development. Why is there this gap between infant intelligence and later intelligence? The usual explanation points to the differences in the content of infant and childhood tests. Tests like the Stanford Binet and Wechsler emphasize symbolic abilities such as language and abstract higher order reasoning and problem solving. In contrast, infant tests focus on different things: manual dexterity, visual and auditory alertness, and so on. Surely, there must be some continuity from infancy to childhood, some aspects of intelligence that remain consistent across all ages. Research suggests that the key might be how infants respond to novelty. Longitudinal studies where children first tested as infants are later assessed for childhood IQ have shown positive correlation between various measures of response to novelty in infancy and later intelligence. Babies who show a strong preference for new rather than familiar stimuli tend to perform well on later IQ tests. After infancy, scores from traditional IQ tests start to show significant correlation from one age period to another. Although these correlations aren't perfect, two key rules help us understand IQ stability. First, the degree of stability decreases as the time period between tests increases. For example, we typically find more similarity in IQ scores between ages 3 and 6 than between ages 3 and 12. This makes sense because the longer the gap between tests, the more opportunities there for the changes to occur. Second, the age at which the child's IQ is assessed also matters. Consider the comparison between the 3 to 6 correlation and the 9 to 12 correlation. Both reflect a 3 years interval, so by our first rule, we would accept them to be equivalent. However, the correlation is greater between ages 9 and 12 than between ages 3 and 6. Generally, the older the child, the higher the correlation in IQ for any given time span. This also fits common sense. As children grow older, major changes in their abilities relative to other children become less likely. The debate over what causes differences in IQ scores, nature or nurture, has sparked many heated discussions. Family studies show that the closer the genetic relationship, the higher the correlation between IQs. But genetic isn't the only factor at play. Children and parents also share the same environment. To untangle these influences, scholars often turn to adoption studies. However, these studies have their own limitations. For instance, the prenatal environment provided by the biological mother, the timing of the child separation from the mother, and selective placement can all affect the results. Findings from adoption studies reveal that an adopted child's IQ tends to correlate more strongly with their biological parents than with their adoptive parents, suggesting a genetic influence. Twin studies also help in this debate. Data shows that identical twins raised together have the highest IQ correlation. Interestingly, identical twins raised apart still have a higher correlation than fraternal twins raised together, supporting the genetic theory of intelligence. One interesting finding is that adopted children often have above average IQs. Why might this be? The most plausible explanation is environmental. Adoptive parents are not a random subset of all parents, nor the adoptive homes a random subset of all homes. Adoptive parents tend to be highly motivated and provide enriched environments such as homes filled with books and access to quality schools. These factors can boost the IQs of children raised in such settings. Thus, adoption studies provide evidence for both genetic and environmental effects. The interaction between genetic and environment is complex. For example, in low socioeconomic status environments, most of the variability in IQ scores is due to environmental factors, while genetic contributions are minimal. In high socioeconomic environments, the situation is reversed. Most of the variability in IQ scores is due to heredity. For example, attending a better school can greatly overshadow genetic differences. In high socioeconomic groups, there is less environmental variability. All children, for instance, attend good schools, so differences in IQ are more likely to reflect genetic factors. One fascinating phenomenon in the study of intelligence is the Flynn effect, which refers to the steady increase in average IQ scores, about 3 points per decade. But what could be driving this trend? One explanation is that the duration of schooling has increased over time. However, this theory has its critics. In the United States, for example, when older and younger siblings with similar education level are compared, the IQ gains remain almost unchanged. This suggests that schooling alone might not fully explain the Flynn effect. Test familiarity is another factor. As people become more Test familiarity is another factor. As people become more familiar to these types of questions and formats used in IQ tests, their performance can improve simply due to increased familiarity. This could partly explain the rise in score over time. Another explanation is nutrition. A 2005 study supports the nutrition hypothesis. which predicts that IQ gains are most pronounced at the lower end of the IQ distribution, where nutrition deprivation is likely more severe. Another theory is that today's environment is much more complex and stimulating. Over 20th century, exposure to various types of visual media like movies, television, video games, and computers have increased dramatically. Each generation have been exposed to richer visual displays than the previous one, potentially enhancing visual analytical skills. This could explain why visual tests, such as Raven's progressive matrix, have shown the greatest increases. Another theory is the lower prevalence of infection diseases. In fact, US states with higher prevalence of infection diseases had lower average IQs. This effect persisted even after accounting for wealth and education differences. This suggests that health factors can significantly impact cognitive development.